you have the building block, you are ready to build up the next step. Okay.
So, all right, now what we're gonna do. Now what we're gonna do is send out a survey for you guys to fill out, and we would like to understand what you guys would like to get out of Learning Labs. So we're going to obviously we're going to help you prepare for this test, but is there anything more you guys would like to get out of Learning Labs? Would you like to see some cool experiments? Would you like to see how a game is implemented in Qiskit? So we'd like to know that stuff. And you guys can fill it out here.
We'll also look into bigger rooms. Sorry about that.
So we'll just take a quick 5 minutes, maybe 7 minutes.
Do you guys think you could put it in the Discord? It's not scanning it.
I'm scanning.
Yeah, we'll put it in.
It's not working very well. We'll put on.
Are you guys okay if I just switch the screen real quick? I need to check something up.
Okay, so while we're just waiting, right? Just gonna get some. And who here has heard of updates or manipulated bits or any phrase like that? Everyone, pretty much everyone. Okay. So basically, our quantum is going to be different than our classical computers. Is that we're going to be changing from the fundamentals. So a fundamental building block of a computer or any computational device is a bit. Right. So in quantum computers, we're going to be dealing with qubits, or quantum bits. Okay. And sometimes they may not work as you might expect them to, right? But it's all because we've been trained to think like this classical way, because most of the stuff around is just classical computation. So if you guys don't understand something right away, just keep in mind it is completely all right. Okay, I was there, I'm still there. He's been there. And it's
I've not been there, I'm still there too.
So yeah. One of the main things that we're going to be starting from is that quantum computing is very much related to linear algebra. And I know sometimes this comes as a scare to some people, right? Because with linear algebra comes its own horrible knowledge. But the most we're going to be doing, right, is going to be matrix multiplication. And if you guys don't know what that is, or some of you don't know what that is, that's also completely fine. We're going to be going over it.
You're about to find out what it's like.
Exactly. So you're going to be learning the skills along the way. No one is this. We're not going to be like, oh, you should have done the reading last night.
Absolutely not. No, we're all here. We're all community. We're all here to help each other get better.
Yeah. So
will there be like a signed reading or not a signed reading, but reading?
Yeah, we'll be giving some supplemental materials, not necessarily assigned, but you can read it on your own to help prepare.
So, anything that we go over in class, there will be, supplemental readings that, usually it'll be from something called a Qiskit textbook. I know the textbook, whatever. It doesn't look like a textbook though. And it'll maybe explain a term or, some procedure in a different way. And if you still don't get it after that, we are open to DMs, anything. Okay?
Yeah. By the way, are you guys all okay getting reported? On this? You guys are all okay?
Are you guys also okay with pictures?
Totally.
If you're not okay, then put it like this.
Thank you guys.
Okay. So, yeah. Everyone here done? Everyone here good? All right. Anyone else still going, or was that quick and easy? Get it done. Looks like everyone's done. All right, so let's begin. So first of all, how many of you guys know how to multiply a matrix? Okay, I see most of the hands going up. Anyone here not sure how to? Okay, so let's go over it. So let's multiply two matrices. And in this case, what we'll mostly be dealing with is elements in A, B, C. All right, so, and then let's just say we have elements X and Y. So, basically what we do over here is this represents one thing in quantum computing, and this will represent another, and we'll go over that shortly. So this is what's known as a quantum state. And this is what can be known as a gate. So before we put actual numbers in these things, let's multiply the matrices out. So what you're going to do over here, in this sense, is you're going to take element A multiplied by element X. And then we're going to add that to element B multiplied by element Y. So what that will turn out is we will get a new matrix. So this is a 2x1 matrix because we have, I think this is a good way to think about it when you multiply matrices. So we have a 2x2 at the beginning, and then we have a 2x1 afterwards. But what we must make sure is that the last dimension over here matches this first dimension. And you can cancel those out, and your final should be this at the beginning and this at the end. So your final thing should be a 2x1 matrix. And so what you're going to have over here is A times B plus X. Or no, sorry. Scratch that. What you're going to have over here is you're going to have A times X plus B times Y. And then in your second entry, what you're going to have is C times X plus D times Y. And so what this means is this is how you multiply a matrix, and this is how you can manipulate states in quantum computing. So we already went over, well, we didn't go over, but we went over what types of matrices you'll primarily be dealing with. So what you'll see over here is the 2x1 matrices, which are known as, well, these are known as qubits. These are the mathematical representations of qubits. They are 2x1 matrices with a value on top and a value on the bottom. So typically, if we want to have the most basic state in quantum computing, we can have 1, 0, and this is what's known as our 0 state. Or other alternate to that is we can have 0, 1, which is known as the 1 state. So these two are our most fundamental states for qubits. So in the case of other states, which can be put into superposition, which you'll see shortly, we may have something like 1 over square root of 2, 1 and 1. And so these are all known as qubits. And some examples of gates include, say, for example, the X gate, which is the classical analog of the coin flip. So say you have a coin facing heads, and that's state 0, and you're to flip it to tails, which is state 1. The way you do that is by applying an X gate.
So with classical bits, right? If we have a 0, you apply a NOT gate and you get a 1. So this is exactly the same as a NOT gate. Okay, so far we haven't strayed anywhere near anything quantum yet.
Exactly. So you can apply gates like this to qubits like this above here to manipulate states. And if you guys would like a physical representation of what qubits and gates could be, take a two-level quantum system, like say, for example, take the spin of an electron, which can be either up or down. So that's a two-level quantum system. And another thing could be a circuit that's cooled to such a low temperature that it can simulate what an atom does. So, and what gates are they can be something like optical wave plates. If you guys have ever heard of half wave plates or quarter wave plates, then that's another implementation of quantum gates. But over here, let's work out some examples of manipulated qubit states. So say, for example, we want to take our 0 state and we want to apply a Hadamard gate. So we can put the Hadamard gate right in front there. So what we can do is, or we haven't even drawn one.
Yeah.
Let's first apply
Do X gate.
Yeah, let's start off there.
Is there any relevance to the difference in strength of 0 to 1?
Yes, we will go over, yes. So it's called rocket.
So these where it's like a vertical line and then an angle bracket, those that's the symbol we use for something called a ket. So kets are used to represent what are called column vectors. So you see how it's taller than it is wide, and there's only one column, so we use this ket notation. And what you can think of this as is we have what's called a 1 qubit state. Okay, and if you have 1 qubit, this right here represents the 0 state, and this right here represents the 1 state. Okay, which might seem like, oh, then why do you have a 1 here? It's flipped, right? But you can think of it as the 1, right? The 1 is a marker of it being in the 0 state, and it's a 0 in this 1 state. Okay. This will make more sense when we get to column matrices or column vectors that have higher or are taller. But for now, you can just think of this as the 0 state or the ground state, and this is your 1 state.
Which can be an excited state in, say, for example, an atom. So if you shine a ray of light and hit an atom and it goes into the excited state, it'll be in the 1 state.
Yeah. So you want to go over how if you do a X gate to.
Do you guys feel comfortable going over complex numbers today, or you guys do? Anyone object? Okay, I don't think so. We'll go over complex numbers then, because that also has to do with rocket notation. So, with quantum states, now we're actually getting into the quantum area. We can have a state that's like this, and this is a very fundamental state, 1 and I. So say, for example, we have a state like that. We could actually represent this state as a ket. So we can assign it the character psi, and this can be represented as a ket. So you can also take the bra of this same state. And so the bra is denoted like this. Oh, that's a lot. Okay. And what that does is this is what's known as the complex, the conjugate transpose of the matrix. So what you do is every element of a matrix, so say for example, just take any general matrix, you have this axis here, and anything that's excuse me a second. Okay, so anything across this diagonal line, you wanna flip over the axis. So the result should be. And we wanna have y over here. We can have f over here, x, and we have z up here. So this is what the new matrix would look like when you're taking the conjugate transpose. And also, any entry that has a complex number in it will be flipped. So in this case, since this is a 2x1 matrix, it will become a 1x2 matrix. So swap the F and G and did I? Yeah, you can. F and Z. F and G. Okay. Swap F and G. Yeah. So. It's still wrong. Oh, no. Okay. Okay, so this is what it's supposed to look like, and thank you for correcting me. What's this thing called again? This is called the conjugate transform. So let me write that. So this is what's known as a conjugate transpose. So if you want to flip a state in a bra to a state in a ket, you have to take the conjugate transpose. So since we have a 2x1 matrix up here, if we want to take the bra of that, we can do it this way. We can do 1 over square root of 2, and we have 1 negative. So this is if you want to take the bra. You also need to complex conjugate. Yes, that is correct. To whoever said that. Yes, question?
What is the difference between the conjugate transpose and the normal transpose?
Conjugate transpose pertains to complex. Well, complex conjugate transpose, I guess we can call it. So
The transpose is just going to be when you flip the matrix over its diagonal.
so
That's just the transpose.
it's like this. So this is the transpose, and also what you want to do as part of it, this is the key part of it. What is it called?
That's just because I joined the Zoom was.
Oh, it's okay. It's okay.
Yeah, it's all good, don't worry about it. So, okay, so what we wanna do is. So, you also want to make all complex entries. Flip inside. So what that means is if you have a complex entry A plus BI, you don't wanna flip the sign of the A. You do wanna flip the sign of the B term. So that should turn into A minus BI. So, in this case,
That's why you're taking transpose.
So here's the thing, just the transpose of a matrix just means flipping, okay? Because,
flipping on this diagonal axis.
yeah, on that diagonal axis. But the thing is that, since we're dealing with quantum and that often comes with complex numbers, we just say in general, if we wanna get the bra from the ket, right? You do the conjugate transpose. If we have a matrix just that's in the real number, like this, you won't do the conjugate part. It would be equivalent to its transpose, just a horizontal matrix
Yeah,
0, 1, right? If I just wanted to do conjugate transpose of this, because there's no conjugate part.
yeah,
Right.
so that's the bra of the one state.
So just to clarify, the conjugate part is taking a complex number and flipping the sign of the complex part of the complex number.
Yeah.
So you just have a transpose, you just flip the matrix, but complex conjugate flips the matrix and also takes the conjugate of every entry.
Okay, so that is basically an overview of what qubits are. and what gates are. So are we ready to give some examples of gates, or does anyone have any questions of any sort? No?
So when you're doing a conjugate transpose, say that the I was in the first position, so the second, would that still be
So, like if there was I here.
Yeah.
And one here. Okay, so when we flip this, right? We're first doing the transpose, so we know it's gonna be flipped. So we have got I here and then one. This would just be the transpose. Like you said, since it's the conjugate, we would apply, would have a negative there. Okay.
Yeah.
And so you want to go to more like
Okay.
gates and stuff?
Yeah, so actually, before we do go to gates and stuff like that, let's talk about qubits a bit more, because this is all just matrix multiplication, some basics of linear algebra. Qubits need to have one special property, and it always needs to be what's known as normalized, every entry in the term. So if we take this state up here, and we have, by the way, the ket is always a qubit.
Yes.
The
So
ket is always representing a qubit, not usually left row, right?
yeah, a state. It's just going to be representing a state. Right now we're just dealing with one qubit states. So the cat is going to be synonymous with one qubit for now.
So if we have this state right here, then what we need to do is take what's known as the amplitude of this and square it. So in classical computing, we normally deal with probabilities by taking probabilities. But over in quantum computing, we have what's known as amplitudes, which pertain to wave functions. And in this case, we need to square each of these terms and make sure that the probabilities, which are the square of the amplitudes, add up to 1. So we can do that by, if we want to sum the probabilities, then we can take the bra of this and multiply it by the, and this is what's called an inner product. So I'll write that down after, but this can be done by 1 over square root of 2, 1 minus I, and 1 over square root of 2, 1 and I.
And keep in mind that in matrix multiplication, order does matter. So
Yeah.
if you have a bra in front of a ket, so sure, there's supposed to be another line here, but since there's 2 lines, physicists just ignore one. So you have put the bra here, so we have the conjugate transpose multiplied by the ket.
Right, that's correct. So we have 1/2. So we have 1/2, and we can do 1 squared plus negative I times I. And that will again give us 1 squared, so that's just basically 1/2 of 2, which just equals 1. So, true enough, the probability, when we calculate it correctly, does always come out to 1. And this applies to each and every qubit, well, probably every qubit.
Is this the square of the amplitude?
Yes,
Where's the amplitude exactly?
the amplitudes are the entries in the matrices.
Okay, so I'll get to that right now.
Yep.
So where else have you guys seen 1 over square root of 2? Or if there was some fancy word for I forgot, but you can also write it as root 2 over 2. Triangles, right? Trig. Exactly. So the reason this is even like related to trig is let's take our 0 state. Okay. Do you guys remember what I said about this 1 and 0, meaning that it essentially is saying this qubit is in the 0 state. That's why it has a marker in the 0 position. Do you guys remember that? So if you want to, he was also talking about the amplitude, right? And measurement, things like that. So whenever we measure a qubit, and we want to essentially it will be a probability, okay, about whether it lands on a 0 or whether it collapses to a 1. So our 0 state, if we measure it, we would want, what does it seem like it would land on? It would collapse to? A 0, right? That's what we would expect. So how you do this measurement is there's a technical math way of doing it too. I'll show you guys the easy way first. So we first want to, since we're dealing with real numbers, all we have to do is square this value, okay? And we get if we square 1, we get the number 1. And we square, we square this, we get the number 1, right? And that will be the probability of this state collapsing to 0. Does that make sense? It's in the 0 state, so it would collapse to 0. And same thing, if you square here, we'll square the 1. This is in the position, right? We square this, we get a 1 chance or 100% chance that this qubit will collapse to 1. Seems pretty uninteresting. It seems obvious, okay? But going along with the definition of a qubit and what makes a matrix a legal qubit is, do you guys remember this formula? This cosine squared plus sine squared is equal to 1. That does ring bells? Okay, good. So in this case, right, another way to write out that definition that Aditya was saying about how when you square or when you do the broad times the catch, you should equal 1, like when you sum them. Basically, the probabilities are what you get when you square the number, correct? You have to square this element, and then this element. So instead of these cosines and sines, we'll square this. Let's say in 0 state, we'll square this. We'll square this. We get a 1. So just like we said before, and we'll see why this makes this is uninteresting states, right? Where you have 0 and 1 state. Nothing quantum yet, but you'll see this law or rule come up multiple times. Okay, and we'll give it a name too.
All right, cool. So those are some important properties about qubits and matrices in general. So first of all, let's give some examples of gates. So gates and special states in quantum computing that you'll see not the question.
Like, is that a bra or a cat is like quantum bit, right? Those, like the other one also a quantum bit? And
Cats are going to be our quantum states.
Yes.
Bras are going to be more a tool we use,
Yes.
right?
They're also quantum states. Just whether you decide to represent them as row vectors or column vectors.
Yeah.
We just like for columns.
Yeah. And it's a mathematical tool that's typically used for calculating probabilities. That's mostly what you'll see for this test at least. So now that we've seen a couple things about matrices, about qubits and gates and stuff, let's go over some fundamental gates and states. So we already went over the 0 state and the 1 state. We also have what's known as the plus state. So that is equal to 1 over square root of 2. And by the way, this thing up over here is called the normalization factor. That's what summation is.
Why don't we go over what is it? What happens when we apply not gate to 0 state first?
Yeah, we'll go over multiplication. I'm just listing first. So we have 1 over square root of 2, and then we have 1. And I'm just listing states out for you guys. We promise we'll get them to you in a much neater way than this. And we also have the minus state, which is 1 over square root of 2, and we have 1 negative 1. And we also have the I state, which is 1 over square root of 2. This was the example we were heavily working with just now. That's 1 and I. And then we also have the negative I state finally, which is 1 negative I. And you guys will soon see how these states can correspond to each other and actually can correspond to games also. So these are all just some important states, and now we'll go over some important beats that will be the most fundamental beats. So we're gonna start out with 4. So the first one is called the poly X gate. So it's called the poly X gate. And so this is a 2x2 matrix, which can be represented as 0, 1, 1, 0. And there's also 2 more. So there's the poly Y, which is equal to 1, 0, 0, right? That's right. Right, sorry. 1, 0,
I
0.
think so.
Yeah, that's the Y. That's the poly Y matrix. And then there's also the poly Z. Oh yeah, what's up?
That's
They're both interesting. Well, matrix is a special mathematical tool, but in this case, they're both. So I should thank you for mentioning that. The only then we have which is 1, 0, 0, 5.
Maybe I've
And
been flipped actually. 0 and y is z as a -1. Y is
That's my fault.
Hmm.
Stuff. So this is Z, this is Y.
Mhm.
Okay,
Here, if you get confused, just y is
thank you.
And y is 0 minus I 0.
use this.
Dr. Davis is here. Hey, what's up, Dr. Davis? Okay,
Yeah, that's our teacher. So
okay, that was kind of a shock. Anyway, okay, let's I guess start with manipulating qubit states. Do you guys feel comfortable doing that? Or
you know the Y gate. All the gates are on my laptop.
shoot, okay. I have to fix a lot of these.
Yeah.
It's been a while. I should have looked at this before. I'm just gonna rewrite all of them for safety, just to make sure all the info is right. Don't wanna give you guys wrong info. Okay. This is faint in my head, I guess. Okay, so these are the real correct matrices. My fault for not getting them right before, but yeah.
I don't know what to do.
That good?
Yeah.
We're all good now? Okay. Yes, that is. Okay, we're all good, just to make sure.
I know some people still writing, but you guys see them? Okay.
So, do we wanna do some basic qubit manipulation?
Start off with that.
I'm very sorry. Okay, so I guess let's start out with basic qubit flip. So, going from 0 to 1 and can go from 1 to 0, we can use the X seed, which is the classical analog of a coin flip. 1 over. So we can do that, and we can also do 1, 0. So this is the X gate acting on the 0 state. So if you don't want to write out matrices, this is how you typically note it. So this would result in the one state, which is 0, 1, and that is one state. So that's the most basic qubit manipulation. And another really important one we'll see is the one that takes qubits into superposition. So this would be using the Hadamard matrix, which, thank God I remember this one. Over square root of 2, 1, 1. So this is what the Hadamard matrix is, and this is what takes qubits into superposition. So we can have this as over square root of 2 as 1, 1, negative 1 plus u. And we have 1, 0. And what this will give us is actually the plus state. So plus state is all the way up here, 1 over square root of 2 of 1 and 1. And another cool thing about this is we can also use this on the one state instead of starting off on the 0 state. So we can have 1 over square root of 2, 1, 1, 1, negative 1, 0, 1. And are you guys comfortable with me just writing matrices next to each other instead of just multiplying them out? Okay, so that will actually give us the minus state.
Okay, so whenever you guys have heard about quantum computing, right? Have you guys heard there being like a term like, these qubits can be in multiple states at the same time, right? That's usually what people hear. So what does that really mean, right? When we say superposition, right, we are alluding to that state of being in multiple at once. But if we do the squaring thing that we talked about, right? Let's take the plus state, for example, and let's do the squaring thing we talked about before, and let's do it on this value, right? So this will give us essentially the probability of this state being, when it's measured, being a 0. Okay, so if we multiply these two, you'll get 1 over root 2, and if you square that, you get 1/2. Okay, and if we do the same to the bottom, we'll also get 1/2. So we're essentially saying that there is a 1/2 chance of this plus state when we measure it, because in quantum systems, measurement is a destructive operation. When we measure it, what we'll see is there's a 1/2 chance of this state coming out as a 0, and a 1/2 chance of this state coming out as a 1.
Can you talk about what a destructive state is versus what a constructive state is? The way it functions? Or not?
No,
Okay,
no.
okay.
So when I mean destructive operation, it just means that like if you in a quantum system, right, if you apply all these gates and you have like these delicate superpositions and all these matrices, right? As soon as you measure any matrix that you'll get, if it measures to a 0, right? That qubit, if you're working with it in a circuit, after that moment of measurement, it'll turn into this if it measured to a 0. If you measured it to a 1, this state. Okay, so you no longer have whatever state you had before. Okay.
Yeah, and the beauty of quantum computing is these complex amplitudes and this ability to take advantage of linear combinations. Yes, question.
What is the negative number?
What are the negative numbers mean? Good question.
So, like you said, it means amplitudes, right? And we're in classical computing, we don't know, we don't really care. Like, what does that even mean, right? So, as you saw, we applied a Hadamard gate, which put both of these, the 0 state and the 1 state, into a superposition, right? And if you do the math, if we do the whole squaring thing, we see that whichever one we measure, both of them will have a 50-50 chance of measuring to a 0, measuring to a 1, right? So it might seem like, oh, so they're essentially the same, right? Why do they have different, why do they have a different symbol, right? But this symbol is what allows, what's different between classical computing and quantum computing, actually, right? So usually when you have a negative and positive, that usually means there's gonna be some sort of addition involved, right? This is what Aditya was referring to before as constructive and destructive interference. So, we won't necessarily like go delve into that right now, but as we, take a look at like more than just one operation on a qubit, right? You'll see why, destructive operations and constructive operations even make sense, okay?
So what happens if you do like a Hadamard gate on a qubit that's already in a superposition?
I guess
It goes,
diving right
it
into
goes,
it.
yep.
Okay.
Walked right into it.
So, that's a good question, and, does everyone feel comfortable with the matrix math we've been doing right now? Okay, great. So, and we can go ahead and.
Yeah, so let's do a Hadamard gate on something that's already in superposition. 1/2, 1 -1, and then we do it on 1/2 on 1. So eventually what's gonna happen is it could collapse. It's gonna collapse to 0. Yes, so it's going to go back to the 0 state. And if you do it on the minus state, so this is acting on the plus state. So if you do this same thing for the minus state. It's gonna collapse to the 1 state.
So, although this might not seem like it just yet, this actually, just what I was talking about, it demonstrates what there's constructive and destructive interference, okay? So, you mind if I?
Oh,
Okay. So, one way we can, write the qubits, does everyone remember, what I was talking about, the, 0 state and the 1 state, correct? And here we have, let's say we have an arbitrary state, we'll call it psi, okay? Like this. We can represent it as okay, don't be scared, there's symbols, but yeah, we'll get to it, okay? So does everyone remember when I was talking about how, let's say, okay, let's get back to that. What did these mean, right? These are just coefficients that you're saying, okay, this is gonna be multiplied by the 0 state, and the 0 state can be written as just this, right? Oh. Okay, it's the exact same as that. And the 1 state can be written as this. Okay, if I had a coefficient that multiplies against the 0 state, where would it show up on our matrix? Right? Would it be this term, if it was, let's say, this is not an actual qubit state, but let's say it was the number 5. Okay, so 5. It won't show up on this bottom, right? But it would show up on the top. Okay. So this would be equivalent to, let's just keep this alpha sign right there. Okay. And then for this other state, it would be equal to this, right? And in the end, we're just adding. Does everyone know matrix addition? Right? Okay. All we're doing is going to be adding the top terms, then the bottom terms. So alpha plus 0 and then beta plus 0. This is what we get. Okay. This is regular matrix. Okay. Now these coefficients, do you see how they directly correspond to the top and bottom values? That makes sense. Okay. So now, you said what happens when we apply a Hadamard to an actual a state that's already in the plus state, right? So what would be a way we could write the plus state right now? So what would be the term for alpha? 1. We could write as, we would have 1, but remember that this coefficient right here,
There's this normalization factor.
we can't forget that. So it would be 1/√2, correct?
Yes.
So we started off in this, let's go back to our side. Zero plus one, okay? And if we go to the plus state, which is we've applied the hierarchy one time, okay? We have this factor, right? And then we have that same factor multiplied to the one.
So in this case, both alpha and beta are 1 over square root two.
Oh, my bad. Yeah, 1 over square root of 2. Okay? And another way we can write that out is by doing this. Right?
Yeah.
0 plus 1 all over the square root of 2. Okay. So now we can apply the Hadamard gate one more time. Correct? And what we could say is, okay, what brought us to this state first? You guys remember?
The original.
The original Hadamard. Exactly. So we know that, and what was the Hadamard applied to? A 0 state, right? So yeah. So we know that a 0 state, you apply Hadamard to it, it becomes this. Okay. Did we go over what a 1 state would look like? We went over the
Yeah, we did.
historical form of it, right? The minus state. Correct?
Yep.
And the minus state, let's just write that out for reference.
Yeah.
Okay. If we had a minus state written in this form, we would have minus. Yeah. Okay. So this is what the minus state would look like, correct? So now, if we know the 1 state, or sorry, the 0 state turns into this. The 1 state turns into this, right? Which will also be written as this. Why don't we apply that same logic to this new state right now? Okay. What happens to the 0 state? We said the 0 becomes this. Correct? We just took the 0 and we turned it into this. Because for every 0 state, if we apply Hadamard, that's what happens. And then to a 1 state, right? We know that this happens. Okay? So we expanded that 0. I have this plus. And we have this all over root 2 still. Okay? Now, you can see that the signs actually might mean something, right? We have this 0, 0. We have this 1, but we have a minus 1 here. Okay? So we're just going to use some algebra. And we know that we have 0, right? And then we have plus 0. And the 1 and 1 would cancel. So divide by root 2. Divide by root 2. If you do that, that would be divided by 2. So you get 2, 0, divided by 2. That cancels, and you get the 0 state. So do you see how we got the 0 state back? But this time, the negative sign has some meaning to it, right?
Yeah.
So yeah, that's a mathematical way of showing that.
Yeah.
This destructive interference.
Yep. And we know we're running short on time, but if anyone wants to stay back and watch a coding demonstration of all of these things, then we're gonna do that now.
Yeah. Yeah. We'll plan out the times better. a bit more.
Yeah, we'll do better
Yeah.
on time next time. We're sorry.
Yes. Question. Oh yes, we will. Oh
5 to 10 minutes.
yeah, 5 minutes. Because Okay, so while I get that set up for
Yeah.
coding, right?
Oh, it's already set up.
Great, okay.
And so, just real quick, this is the terminal for IBM
I'll just do drag and drop for now. I'll do coding.
Composer.
Yeah.
Okay, then yeah.
So the reason why matrix multiplication is important is because when you apply a gate to a qubit, as we saw, we're gonna be just putting that gate in front and multiplying. Okay. So what we can do is on IBM circuit composer, this is the first step before we code, is we can just drag and drop gates. Okay. So if this is what the X gate looks like. We just drag it, we put it on there, and we can see that.
Here, let me delete one qubit, so we just work with one for now.
So all qubits are going to start in the ground state, so the 0 state, okay? Like we talked about. If you apply a NOT gate to that, just like in classical computing, it flips to the 1 state.
Right.
So you can see on the right, we will teach you guys all about this stuff.
That's all chasm right there.
That's good.
Is it? Oh, yeah, that is.
So
It's usually chasm.
what IBM does for you, right, is if you are first learning, which is really helpful when I was studying for the test and all, if I wanted to know what it looks like just applying an X gate, okay, they initialize a quantum register or whatever, right? You do circuit dot X, right? And you get whatever index qubit you want to work with, and it applies that gate. Okay. So the reason I'm telling you guys this is because when we start going over coding and stuff, and if you feel lost, like one of the best things to do is open this composer up, and you say, okay, I'm working with a qubit in the 0 state, and if I apply an X gate, I just drag it. What happens? I want to know what that looks like coded. IBM will code it for you.
Yeah, and you see the code all on the sides, and if you want to do a simulation here, you can drag and drop it, and you can also run this. This is another way to run a job. So you can run these either using simulators or real IBM machines.
Okay, so that would be it for today.
Yeah, so real quick, we'll use the composer. We'll get you guys set up with Qiskit more next time. So that will be in 2 weeks from now. See you guys later, and we hope this is really helpful.
We're probably gonna send out like a form for like feedback, right, on session length and how often you guys want to meet.
Yeah.
And now that you've gotten like a taste, whether you want it to be a bit more fast paced or even like longer or more frequent meetings, we'll send that out and we'll get your feedback on it.